So, so today we'll cover the last of our site investigation topics in looking to define aquifers and aquicludes, which has been kind of the general theme, so that you come up with the pictures such as you have in your assignments, which have to come from somewhere. They come from site investigation, because otherwise you're standing on top of a field and know nothing about what's going on in the subsurface. We talked about direct methods of investigation, trenching, not used very much, but drilling to get through soil using solid stem and hollow stem augers typically, drilling to get through soil and rock, which is tricone rotary drilling typically, and drilling to get through rock only and recover core, which is rotary coring. So we talked about each of those. Of those, only rotary coring intrinsically recovers a sample, which we'd like to have. That was 7.2, we talked about sampling. So rotary coring would give us samples directly. Tricone drilling would kick drill chips up the hole, and with the return fluid, either air or drilling mud or water, where they could be sampled, collected and sampled, and kept as a definition of what's in the subsurface. And in soils, we talked about using split spoon and Shelby tube samplers. Split spoon for sands and gravels that are banged into the ground, Shelby tubes for fine-grained materials, cohesive materials, clays and silts, which are pushed into the ground and which allow you to retrieve samples to take back to the office. And we closed out in talking about direct push methods as well to use as an analog. And so the observation for those methods of investigation, I guess, is kind of picked out in this little figure here, is that it's great that you have really detailed information along the line of a borehole, but that borehole might be a really very, very small percentage of the site that you're trying to figure out what's going on. And so a piece of core may be the size of your fist. There may be a continuous record of them, as in a rotary hole, a diamond drill rotary hole, or it might just be sporadic locations that you have it. And so the question is how you might want to fill in the dots between those locations. And so geophysics is one way that you can basically do that. And so geophysics is using some proxy, just not get larger. Doesn't, oh it does, yeah, fine. So using some geophysical proxy to be able to be indicative of a particular stratigraphy or fluid that's in the subsurface, and then ground truthing it against the drilling that you have that is an actual sample that you know physically what it is, and therefore you can link the two. So the signals that they would use would be the magnetic properties, the magnetic field in the earth, using the conductivity or resistivity of the subsurface to define what kind of soil or fluids they are, using the acoustic velocity of the materials in the subsurface, the seismic velocity, or by using the density of the stuff underneath your feet to be able to do that. And each of those can be used to be able to fill in the complete subsurface, tied in by a few boreholes, as we saw earlier, and therefore construct a picture of exactly what's going on. The final one we'll talk about is maybe using logging tools in a well bore to be able to measure each of these properties, the magnetic properties of the materials, the electrical conductivity, the seismic velocities, or the densities of those materials, to be able to link up with the subsurface. So we'll talk about each of them in turn. It's probably not that you're going to be specialists in these areas, but you might contract a provider to go on your site to be able to do a survey, and you might have to interpret the results. You might have to choose what kind of method might be appropriate. So understanding something at least in overview about these is important. So we'll go through each of them in turn moderately rapidly just to give you a feel for what they are. So geomagnetic methods, they basically rely on the fact that if you look at the Earth has a magnetic field which is driven by an iron core in the center of the planet. And this has a polarity which your compass picks up. And it's lines of magnetic potential that circle the globe and enter into the Earth at some particular inclination. So these lines of potential representing the magnetic field, if they strike something which is metallic, then they will bunch together. And if they bunch together, they will tend to attract the lines of potential through that ferrous target, iron target, such as buried barrels, 55-gallon barrels. And if it's concentrating the potential through there, then it depletes it in the area to the side of it. So if you can walk across a traverse that cuts across this, and you can measure the magnetic field as you go across that traverse and plot it, and what it might look like in terms of Teslas would be that if you are have a deeply buried object, you might be able to pick it up slightly. As you have those objects closer to the surface, or if you survey closer to the objects, then you get progressively more definition. And so by picking up changes in the natural magnetic field of the Earth, by walking over it, you can actually say something about the material underneath you. So you could look for iron drums, which might be the sources of the contamination that you might have found in wells downstream. You can use these methods somewhat quantitatively. And so because of the inclination of the magnetic field, if you have a target which is present at depth, then the signal that you'd pick up for that target would be a bit of a skew bell curve. It's skewed because the incident magnetic field is not coming in directly vertically, in which case it would be symmetric, but it's skewed and therefore it defines a particular shape. And you can identify the location of the target by the inflection points, the peaks and the troughs of the distribution, and also say something about the depth of burial as a result of this. And so this is a very quick and commonly used method to be able to prospect for metal targets in the subsurface. The instruments come in two flavors, permanent magnetometers, which are you set up on site and you almost the size of the cover on a theodolite, and you carefully make it horizontal, and then at that particular location you measure the Earth's magnetic field to nanotesla, very small gradations, and then you reposition it at another location and then keep on doing that to be able to fill in the individual components of a traverse. The much more common way of doing it is to use a so-called proton magnetometer. And proton magnetometers are, or look like, this. Is this one? Yeah, okay. Would be something that looks like this. Can't really see it very well. It's an instrument that has a coil around it. It applies a current to the coil, aligns the hydrogen nuclei and water in there, and from that it can measure the magnetic field. You take this and you physically locate it at multiple locations. It's attached to GPS to be able to locate where you are, and as a result of that you can put together some kind of profile that looks like this, or that maybe looks like this, which allows you to get some granularity of exactly what's present in the subsurface. So quite commonly used. But you're looking for metal targets, not for anything else other than that. So if you don't have an iron, a ferrous source, an iron source, then you won't pick up anything. So it's not very useful for looking at the individual characteristics of the subsurface. So, using the changes in the Earth's magnetic field due to magnetic components in the subsurface is the first proxy, I guess, for something that's going on. Geoelectric methods come in two flavors. They come in DC methods, as in direct current, and AC and electromagnetic methods. And they measure the resistivity or the conductivity. One is the reciprocal of the others, of the material in the subsurface. So the basic idea is this, that if you look at Ohm's law, U equals IR, so U is voltage, which is potential, change in voltage, well, it's voltage, between two locations, across a battery, for instance. I is current and R is resistance. If you think of that measured across a resistor or a conductor, resistor as in a circuit, then usually it measures the change in voltage drop, delta U, I guess it would be, which is a voltage drop between upstream and downstream. And it measures it across a component, and that component has a resistance, bless you, which is defined in ohms from your physics classes. If you look at the subsurface, you can treat the subsurface a little bit like Darcy's law. Velocity is equal to hydraulic conductivity dH dx, which is, oh my goodness, is pollen coming out? I've always got your well-being at heart, all of you. So Ohm's law is, again, I equals 1 over R U over the length that it's applied. And how is it going to be? This is resistance, and this has to be a velocity, I divided, this is going to be added divided by Q. So Q is too much information perhaps for you. Q is the cross-sectional area of this. B is the length of this, which is this. Merely to say that the current, which is amount of amperes, I guess, per unit area, is the same as the flux of fluid, the velocity. The potential gradient, the change in head with length, is the change in voltage over the length over which it flows. And 1 over R, if we rearrange that so that we get is equal to B, has to be, I guess I'm adding these. So this is I U over B, and this would be left with B over R, and I divided by cross-sectional area would leave Q. Yeah. So this term here, this is current, this is voltage per unit length, so the potential gradient, just like Darcy's law. This term here is not resistance, not 1 over resistance, but the whole term here is actually specific conductance. Actually, let's call it conductivity. So this is hydraulic conductivity. It's the measure of the bulk properties of a porous medium in terms of its transmission characteristics of fluid. So this is the electrical properties of a porous medium, not a resistor, defined in terms of its resistance, the length of the sample, and the cross-sectional area of the sample. So specific conductivity is the reciprocal of specific resistivity, and the units in which it's measured is in ohm meters. So just because of the units of this that came here. And so the idea is that what you could do is you could take a voltmeter into the field, and you could take a battery. And so if your battery allows you, so if you put a piece of rebar into the ground at points A and B, and if you have a voltmeter, the same kind of voltmeter you could buy in the store, and you put two pieces of rebar in at M and N, what you could do is you're putting 12 volts from a car battery, which is essentially what it is, into the ground. If you measure the potential difference between those 2 points B and A, has to be 12 volts if it's a conductive cable and it's a resistive geological medium. Then if you measure the potential drop between M and M, they'll be less than that 12 volts. So what you could do is you could use that measurement of the potential drop between those locations, bless you again, and take this to be able to have this array of these individual components and physically expand it. So if you take A and B and you double the separation between them, and you double the separation between M and N between them, then what that would do is that it essentially, since you're sampling, you could imagine that sampling between these samples the intermediate area between them. So as you increase the separation between these A and B, you'll progressively be sampling deeper and deeper into the subsurface. So what you do is by physically being in one spot over one location, it could be on top of where you drilled your borehole, you step out with these individual probes in the ground further and further. As a result, the voltage that you measure as M and N get further and further apart will be progressively deeper and deeper. I guess M and N here would measure this one. If M and N were here, they would measure this one, progressively deeper. If they were here, they would measure even deeper. And so as a result, you're basically doing a sounding to be able to get the profile of the specific resistivity of the porous medium with depth. And so you can do that. There are different arrays of these that are used. Sometimes they're used with the separation between where the voltage, where the current goes into the ground at A and B, and where you measure them are in different configurations. It might be that you physically move A and B, double the width of them, and double the separation between the middle ones as well each time. So you move it out. The next one is 2A and 2A and 2A, and take a reading. And so that these different configurations. And so what you do is you measure the voltage, the current that you put into the ground, which is due to the car battery. You measure the voltage drop between these inner components here. You take the ratio of them and you correct it with a correction factor. And this correction factor allows for the configuration of all the electrodes that you do. So it's really just sampling the geometry of the electrical flow field in the subsurface. So you take a measurement for the voltage at each of the separations, you convert it. The different configurations are called Venner arrays, dipole, and Schlumberger, of course, is where the company Schlumberger, the two French brothers who invented this technique, started their activities in the oil service company by the same name. And so you can use it in two modes. You can imagine doing it in this mode, where you take a location and you expand the individual arrays out to the side and do a depth sounding. Or you can imagine doing it as a single template and just taking that template and physically moving it across a section. And so that kind of behavior is kind of shown here just by schematic. So you take this array with these inner measuring components and the outer measuring components, and you measure the behavior maybe at this location here. You take that template and you move it 100 feet over, then 100 feet over, then 100 feet over. So physically you're measuring the electrical resistance below that array at each of these locations. And if you plot it with location, you can pick up some kind of feature that you've all of a sudden discovered that would have a higher resistance or a lower specific conductivity than the material around it. So it might be a clay or a fault that has water in it in something else that has a different resistivity. Or alternatively, you could use it statically to sound. So you start off with one measurement. You take the voltage between these locations at the inner portion relative to the current that's going into the ground. Current that's going into the ground, measured voltage, some kind of correction depending on the geometry. And if you do that at this particular separation, then you get some idea of the resistivity at this particular location. You take it out by expanding the array, but at the same point, and that gives you a value that represents this, and would be this here. You take them out to this final stage here, and that would sample something like this, which might be overall representative of that particular depth here. So you'd get single values of the resistivity for each of these points, and then you have to interpret this resistivity in terms of the change in resistivity with depth, which is some indicator. Resistivity is a proxy for the geology. And so you can use it to pick up a plume, which might be conductive. Say sodium chloride plume should be conductive. You can pick up metal objects in the subsurface, which are conductive. Or you can also pick up changes in lithology, because different soils and different rocks have different electrical resistivities. If you know what the resistivities might be, you can make a guess if you have an absolute measure of the resistivity as to what that material will be. And so tables exist with magnitudes of these individual resistivities for all kinds of materials. For soils, clays and sands, for building rubble, for rocks, limestone, sandstone, gneiss, and also for things like garbage, refuse in the subsurface, which you might be looking for if you're looking for an individual landfill. So you have some idea of what the ranges of those values are. And so the problem is that those ranges are overlapping for many different types of material. So they're somewhat ambiguous. And so it's unlikely that you just do a sounding and immediately be able to tell what's there without knowing in advance what might be there by having a drill hole that's previously sampled it. But of course, the advantage of this is that if you do have a drill hole that samples it, you can ground truth on that drill hole, and then you can do this sounding much more inexpensively than drilling other holes on other portions of your site. So that's the mechanism of doing that. You get some kind of profile of apparent resistivity with depth. You can convert that by inverting it to be able to get a profile where that profile is composed of, bless you, good God, of discrete packets which have stratigraphic boundaries at different depths and with specific electrical properties. And so the problems are, if you have a conductive layer at the surface, it'll tend to mask everything that comes below it. So it becomes a bit diffuse. And the second one is that the solutions are not very unique. And so if you calculate what the resistivity profile with depth was for each of these sections, which have similar materials in them but different thicknesses of them, you'll get roughly the same recovered section. So if you have a model that allows you to calculate what the distribution of resistivity was for each of these profiles, they'd look largely the same, and they'd look largely like this. And so choosing between those really relies on the fact that you might want to have one well bore that goes down through your stratigraphy, says very definitively that you have this stratigraphy at these particular depths, and allows you to exclude these other material properties which are present and focus on this one. So it's a relatively straightforward way of doing that. You can also do it, you could imagine this idea of having interior and exterior electrodes. So these are two interior electrodes, two exterior electrodes hooked up on the outside to a 12-volt car battery, a voltmeter on the inside. Instead of doing this, you could imagine having it not in a straight line, but doing it azimuthally. And so you could imagine setting up an inner electrode and an inner electrode, and outer electrodes and outer electrodes. So this would just be one section across this. The two inner electrodes for measuring voltage, the two outer ones for putting current into the ground, and do a profile for that. You could then, instead of going out laterally, you could twist it azimuthally. And if you twist it azimuthally, it would measure directional resistivities. And so you might want to do that if you think you have fractures in the ground. Those fractures are filled with water, which might be conductors, good conductors, and therefore would have low resistivities. So as you work your way around this azimuth and plot the magnitudes of resistivities, you might get different magnitudes. And so a picture of that, actually you can't see it very well, and I think I only have one, is exactly that here. So you can see some spikes in the ground. You can see some instruments that allow you to measure the voltage between these inner electrodes. And this is arranged in a circle so that you can go around an azimuth. It's somewhere in Wisconsin. It's in clay till, and you're trying to pick out the conductive features, which are fractures. And you're interested in those is because they're fast pathways for groundwater. I also pulled up this. So the equipment is this kind of behavior. Car battery, usually not your car battery, but a car battery you take. Electrodes that are put in the ground to be able to put current in and to measure voltages between them. And this is measuring the voltage and also the current that's going into the ground to be able to get this ratio of uppercase U over I. Uppercase, the voltage over the current going into the ground. Very simple, very simple. So, geoelectric methods. The other way it's also used is for electrical, so-called electrical resistance tomography. And so this is Edwards Air Force Base. Don't they land the shuttle there? Didn't they land the shuttle there? I guess no more. In California with a long runway. This is a cleanup of a DNAPL contaminated site. And the idea is that at this site, what you could do, you have DNAPL got into the ground, fractures, and I think they were remediating it by steam flushing some boreholes to be able to vaporize the DNAPL in place. And one question that you have is whether you've actually cleaned up the site or not. And so one way to monitor that would be to do the remediation by injecting steam, but also have electrodes or sequences of electrodes in the ground that are placed along maybe a well bore at different locations. Maybe well bores on two sides of the contaminated site. And then you measure electrical resistivity between each of the two pairs in sequence. So just like a medical X-ray where you use electromagnetic radiation, you're just measuring the electrical conductivity between them. And once you have the electrical resistivity measured between all of these points by doing all of them in sequence to go across, so you have a complete network of this, you invert all these data to be able to say piecewise within here what individual block electrical resistivity is. So you have a color map, if you like, of the electrical resistivity. And if you can relate that electrical resistivity to the concentration of the DNAPL which is in place, you have a way to be able to convert that to maybe the saturation of DNAPL or concentration of DNAPL which is in place. So that's what these are. It's a black and white rendition of a color photograph, so it doesn't come out well. But basically the idea is to be able to do a CAT scan of the electrical resistance in situ. So those are electrical methods, DC electrical methods. There are some exotic ones which involve using electrodes to put current into the ground, then turn it off and look at the decay of the voltage in the ground. They're not used really very much for contaminant hydrology, so I probably won't talk too much about them. There are other electromagnetic methods which use a big transmitting coil and a coil which measures the induced electromagnetics in the subsurface. They're usually used to pick up electrical targets and big electrical targets, as in looking for ores or perhaps critical minerals these days. Again, they're not really used in environmental geophysics, and so I won't perhaps talk about those. And again, time domain electromagnetics are the same. You turn on a current, turn it off, and you look at the decay of that current in another body. So they're not used very, very much. So geoelectric methods we talked about. Ground GPR, ground penetrating radar, quite commonly used. Pretty straightforward. Works on the same principle as air traffic control. You have a transmitter, sends out electromagnetic wave, radar wave. It hits something, it bounces off and comes back to a receiver. For air traffic control and also for these instruments as well, the transmitter and receiver are essentially the same location. So this is a very narrow angle between these. And you just measure the difference between the transmission initiation and the reflected time that comes back. You know the radiation travels essentially at the speed of light in the subsurface, as it does in air, slightly different from that. And if you measure the travel time, the two-way travel time, you can pick up the distance of this interface. It'll also keep on going and carry on and be reflected on other lower interfaces. And these are the same things that if you watch any of these archaeology shows where they're looking for buried bones and where did I see it? This looks like seismic. Oh, I thought seismic came first. This is what they look like. It's just a trundle. It has a transmitter in the subsurface in this trolley. It has a receiver right in front of it. You push it across the surface. Sometimes they're on vehicles. They're on a quad bike or something. You get the signal up here. It uses GPS to locate where the individual, not sonar pulses, which are acoustic, but the individual pulses are sent from. So you end up with a continuous profile of the system. So what they look like. So it relies on the transmission of a radar wave, which is an electromagnetic wave at a specific frequency. Usually when you use these instruments, you can change the frequency of the antenna because higher frequencies have less penetration but more resolution, and lower frequencies go deeper but don't tell you so much about the details. It depends on the dielectric constant of the material in the subsurface, which is the capacitance of that material over the capacitance of a vacuum. And differences in the dielectric constant of different materials give you an interface. And so if they're all the same material, there'll be no reflection. But if they're two different materials with different dielectric constants, they will cause an interface, and that is what you see. The actual dielectric constant doesn't matter so much in terms of reducing the data, but there have to be a contrast to be able to get a reflection. And the depth penetration that you get depends on the material you have. Shallow in clays, super deep in ice or water. Okay. And so typical dielectric constants are here. They don't matter so much so long as you've got a contrast. And the main thing that matters is that you know what the two-way travel time velocity is. So these are in meters per nanosecond. So they are essentially the speed of light, not meters per second, but 10 to the minus 9 seconds. And they vary a little bit. I guess they vary by from a 0.3 or 0.1 to a hundredth. So they vary by a factor of 30. Yeah, 30. They vary by a factor of 30 to be able to reduce data. And the way that you'd want that these recordings come out is that you run your buggy over the top of this surface from left to right. At each of these locations, it sends out a pulse, and this pulse reflects back to the surface from a whole variety of different depths and is given an output like this. And you try, if you go across the location of a borehole, to be able to locate the interfaces that you see. So here's one interface, which is here, which picks up with this. This is an interface here, which is this, I guess, this strong reflector here. This is an interface here, which I guess would be this one here. And actually this is, I don't know what the scale is here. So this is 3 feet of river ice on the Mackenzie River. This is 6 feet of water in the Mackenzie River below it. This is silt that is present in the base of the river. And then this is rock, solid rock below that, with this chirp signal across here. So the fact that you've drilled an expensive drill hole, this was the drill that's on the front of the canvas picture for this course, sitting on the ice. The fact that you have this congruent with the drill hole is you absolutely know what these components are and what these signatures are. And so you can extend this across to be able to say that this portion here where the eroded rock level rises to meet the base of the river at this particular location. So it allows you to be able to demark that. Is used in environmental geophysics to identify both geological interfaces, which is done in that case we just looked at, but also pick up things, other reflectors which might be buried human objects, and to reduce that data. So again, some idea of the individual components and some idea of the stratigraphy. So seismic methods, so we've talked about using how the conductance, the magnetic conductance of objects in the subsurface changes the geomagnetic field. We talked about the electrical characteristics of electrical resistivity and conductivity are a proxy for geological media. We talked about the varying dielectric properties allow us to have reflectors for radar, for electromagnetic waves in the subsurface. So those are 3 useful signals. The fourth is the acoustic velocity, the speed of sound in rocks and soils. So typically of the order of a few kilometers a second in rocks. And seismic profiling methods measures the seismic velocity in the subsurface and tries to be able to identify interfaces which have different seismic velocities in them. That's all. And so you hope that individual units with different seismic velocities have different fluid transport properties, or relevant properties that you're interested in. There are three forms of prospecting, I guess actually two forms of prospecting. One is by seismic refraction and one is by seismic reflection. And they rely on the properties of seismic waves in the subsurface. So if you have, for instance, a piece of dynamite that you set off slightly buried in the ground, it will make acoustic waves which will travel both on the surface but will also travel in the subsurface. When they hit something that has an acoustic contrast, so the product acoustic impedance so this is density. Not very good writing. The bulk density of the material and the acoustic velocity. In the same way that dielectric constant was the feature that made radar waves, electromagnetic waves, bounce off a surface, contrasts in acoustic impedance, the product of acoustic velocity, seismic velocity, and density of that material provide the reflectors that reflect waves. And so when an acoustic wave hits that surface, it does one of three things. It is either reflected back from it, Bragg's law. It comes back at the same angle of reflection as the angle of incidence. It either reflects along the interface and then potentially comes back up at this same angle that the reflection came, or it is diffracted deeper into the subsurface. This acoustic energy is lost, and so we don't really care about this, but both the reflected wave and the refracted wave will end up back on the surface. So if you think about putting along the surface a whole bunch of geophones, which measure the arrival time of the acoustic wave, the pulse, then you can use that information for both refraction and reflected waves to be able to say something about the acoustic velocity, but also about the depth of the interface that you're looking at. And so for reflection, the acoustic waves, it's exactly the same as this. You get a two-way travel time going downwards and coming backwards. If you know how long it takes to go from this interface back to the source, then two-way travel time and the velocity gives you a length. Velocity is equal to length over time, nothing more than that. So length is equal to velocity times time. The time that you get from the transmission to the reception is the two-way travel time. So I guess you'd want to divide it by half to get the length, because the length would be the two-way travel. So for seismic reflection, you'd use the acoustic velocity to do that, to do this. And so usually in environmental geophysics, reflection was the most commonly used method. And so the best way to show exactly what this would be is that you have a source on the surface, and you'd put a whole bunch of geophones along the surface to be able to record the first arrivals. So this might be a stick of dynamite buried in the ground that you set off. It has an acoustic wave that goes into the ground and is reflected. And so this geophone would record the travel time, which is relevant to this passage of this wave, and this would give you a travel time T1. If you locate where that geophone is, and you measure the time it takes to travel, this is the length in this direction, and this is the travel time here, and this is zero travel time. So if you set off the shot at this particular location here, the travel time's 0 if you're monitoring it. But if you're monitoring it at geophones on the surface next to it, you'd get some pulse of the first arrival in each of these geophones as you go across the length here. And so the idea is that if you shoot at this particular location here and you measure the first arrivals, then you get, for each of these geophones, the first arrivals would be at these locations. But from this first geophone, it picks up the reflected wave. It goes down to the interface, bounces back. I guess the first reflected wave would be here, but you don't have a geophone here. So it's measuring the reflected wave. This is also measuring the reflected wave, which is, actually no, it's not the reflected wave. It's the transmitted wave that it goes along the surface between these points here. And so that would be the velocity. This is a length. This is a time. So the seismic velocity is equal to the length traveled in a given time. So if you have both the location of the geophone and how long it took to travel, by definition you have the seismic velocity between these. That's what it's measuring. But once you get further away, the first arrival in this point, instead of going in the seismic, so V1 is less than V2. So if the seismic velocity in the lower layer is faster, it would rather go down to this fast layer, go along it, refract back up through that layer, and be registered at this geophone. It's the fastest way it comes. The wave that comes all the way in the slower media and arrived here would arrive later. It's not so obvious here, but if it comes all the way to this geophone here, it would be the direct wave along the surface, and it takes longer. So this wouldn't be the first arrival, because this is time. The first arrival would be the one that would go across the slow layer, get into the fast layer, refract along its base, and then re-refract up through the slow layer to give you this area prime. So the information you now have from this is that now you also have a travel time and a length, delta L. So this would be a proxy for the velocity of the lower layer. This would be V2. And so if you have these data, the slope of this will give you the velocity in this uppermost layer. The slope of this will give you the velocity in the layer below that. And the inflection point where it changes from one to the other gives you the depth of this layer. I won't go how to do that, but you can get those three pieces of information from it. So if you do this at a single shot point and have some geophones, if you then move the shot point to another location, which would be here, and do that same measurement, you can use this information to say something about both the velocities of these individual layers and the individual depths of them to be able to recover that from the seismic profile. So it's a little convoluted because it's using this idea of refraction. And the reason it used to be that refraction was used in environmental geophysics is that these layers are not very thick. Maybe they're a few meters, 10 meters. And so you needed to measure very at fine resolution the arrivals to be able to resolve velocities across the fast incoming velocities. With instrumentation now, that's not such a big deal. And so seismic refraction is used, but also seismic reflection is used. And seismic reflection is just the opposite. So this uses exactly the same as radar. You have a transmitter of an acoustic wave, not radar, and you have a receiver. It might be at the same location. So you get this two-way travel time off this reflector and off any other reflectors below it. And so you end up with this kind of map of all of these reflectors, and each of these are just the two-way travel times to get to the reflection from this place. So the two-way travel time, so this magnitude here on this side here would be the two-way travel time. The time for it to go down to this interface and then back up to the receiver. So that would be what this is. And so now reflection is also used in shallow geophysical surveys. These have always been used for oil reservoirs, which might be, this depth would be 1,000 meters below ground. Marcellus is at 3,000 meters in Pennsylvania. And so you can fill those in. And so seismic methods are just a method of doing an experiment to be able to measure the distribution of the velocities and the depths of those velocity layers of the subsurface using a recording system which is something like this. Can't see the, I don't know if you got pictures. Actually, that's exactly this. So you can, it's tiny. Well, let's look at the photographs. What do we have? This is Montserrat, that same volcano we looked at before. This is 20 years ago, so not very modern equipment. Comes from a university. This is measuring, this is a GPR device pulled along, transmitter and receiver, pulled along between two locations of constant distance between them to measure the behavior. This is a geophone. So usually it's a geophone is just a spike with a unit on the top, and this yellow unit just contains a coil that sits inside a wound spindle. So when this coil within the wound spindle moves, because this is being shaken, then it generates a voltage. So just like a electrical motor really, except it's being shaken rather than turned. And it generates a current which you can record. And so this would be a string of geophones attached to a single trunk wire. They're attached with crocodile clips onto the trunk, and then the motive explosion in this particular case is a sledgehammer with an electrical cable to the sledgehammer and a plate. That plate is attached to a battery so that when you close the circuit, it immediately gets the impulse, the timing of the impulse, which then is picked up on the individual geophones which go into the surface. So yeah. So the geophones would be laid out along a length. They'd be connected along a trunk line to be able to gather all the acoustic signals, the first arrivals, and then that information would be initiated by providing something into the ground that is big enough to be recorded. Typically, sometimes with a sledgehammer, sometimes with an explosive. This is an even older seismograph. These knobs are just for the amplitude gain, to the amplification of the signal, and all of the information from the individual geophones would come in on this cable. These are some older geophones that are just pushed into the ground. They have a conical tip, so you can bury them. This is in western Alberta. These individual lengths of cable have crocodile clips on them to be able to fit on a long spool that's lent out. This is the spool on someone's back. It's being carried out. This is detonator wire to be able to run a shot. This is that instrument, and this is the shot. In this case, it's a quarter stick of dynamite in a beaver lake, I guess. Not sure how environmentally responsible that is in this day and age. So that's maybe from, it is from 35 years ago. This was from last Friday at a limestone quarry in Mechanicsburg, next to the Tesla dealer, which had 200 people picketing it outside when we left in the evening. And this was, I have a picture somewhere. This is a limestone quarry. If you look on here, this is a bench with all the, these little white points are drill holes, which are drilled as blast holes. So each of these drill holes are filled with ANFO, ammonium nitrate and fuel oil, and then stemmed in to seal the tops with detonators put in them. And these are used to blast the bench. This bench here is missing and has been blasted. And so this actual project was to look at a single TNT hole here and a hole that is filled with a carbon dioxide gas gun as a way of fracturing rock to get for hydrogen production. The new thing for renewable energy now is creating hydrogen from iron-rich rocks, so you have to make surface area. And so this acoustic array was sent out to monitor the blast. And so the acoustic array, this is what a geophone looks like in my hand. 3 prongs just to stick it into the ground, about the size of a can of tuna, I suppose. 3 components. It measures left, right, and up and down. And it's attached to each of these. Each one of these is a little bag that it comes in. It has this geophone in it. It has a recording unit, which is battery powered and completely independent of the other units. It's run by a GPS clock attached from a satellite. I guess I'm going back here. You can see them laid out actually along here. So this is, underneath this bag is this geophone. This line here is optical fiber. So the same as you get your telephone calls on optical fiber if you're on a landline. This is just a piece of fiber optic cable covered by about 4 inches of tailings, limestone tailings. And you know that fiber optic cable can actually pick up the sound waves in exactly the same way as these geophones do, except it doesn't give you a single geophone every 5 feet. It gives you a geophone every millimeter or so. And so it's a huge data density. And these are infrasound sensors, essentially microphones to pick up the air blast that came from this. And these were arranged linearly. So this is the measuring equipment. I'm not sure whether I have pictures of they're all arranged along a line. This is the borehole that is TNT loaded and Cardox loaded that were blown, and the acoustic signals were measured at those particular locations. So this is the borehole somewhere here. This is the line of the geophones, these yellow sandbags weighting them down, and the microphones measuring the air blast. That's it. This is an electrical resistivity, a car battery, and measuring the voltage between these 2 locations. So how are we doing? 22, we got a little time. So the final things maybe to talk about. So we talked about seismic refraction, and seismic reflection, how you get that. Gravity methods, not much is used there. The idea is that if you can measure very locally and very accurately the gravity at every point on a traverse across the ground, just by measuring the force in a spring as it dangles a weight, the force in the spring will be larger if gravity is stronger in a particular location. And so if there's some mass missing in the subsurface, like a tunnel under the demilitarized zone between North and South Korea, you could use a gravity survey to pick up the fact that there's mass missing in the subsurface. So in other words, a mass would not be attracted so much to that zero density zone, and so you could measure a reduced force in the spring, which would represent the fact that there's some mass missing here. And so if you're looking for karst cavities and caves in the subsurface, which might be conduits for flow, then you might use gravity surveys to be able to pick this out. All it is an instrument like a theodolite. It goes on the ground. You level it with the tripod legs, and you use it to pick up the gravitational field at that particular point. The problem is that when you measure the gravitational field, that gravitational field is affected by lots of things. It's affected by where you are on the planet, your latitude. It's whether you're at sea level or on the top of a mountain, the topography that you're on, by earth tides, and also the density at depth, which is the one signal you want to measure. But these other four, if you like, confounding factors have a big influence, almost as much as the signal you're measuring, and it tends to not be a very precise way of. It's a difficult measurement to make. So those are the different geophysical proxies that you might want to measure on the surface. And the idea, as we mentioned, was we'd like to be able to fill in on the whole site the behavior of proxies of materials that we can ground truth with boreholes. And those proxies that we're interested in are the magnetic properties of the subsurface material, the conductive or resistive properties of them, their acoustic properties, their velocity, the speed of sound in rock, or their densities, which are the proxies. We can ground truth these, as we've mentioned, against a borehole to be able to say what's going on. But the other thing we could do is also we could measure them directly in situ. And so I don't know whether it's used very much in environmental geophysics. It's certainly used all the time in petroleum geophysics, and that is well logging. And so well logging is merely the idea that within the well that you have, you would take a sonde, which is just a thin instrument, not so different from this perhaps, which is on a wire line, and you just drop it down the borehole, and the wire line has a cable which gives you the signal up to the surface, and it measures some geophysical signal as it gets transited down the borehole to the bottom, and then the same repeat as it comes back out. So that signal might be by having a bowspring on the side to push the sonde against the wall. So you could have a little seismic pulse go into the wall, it travels along the borehole wall and is received somewhere along the sonde, and that you can therefore measure the seismic velocity at that portion of the wellbore. And if you're passing the sonde all the way down to the bottom of the hole and pulling it back up, you can get the complete profile of the acoustic wave. So you can do that. You can imagine you could measure the electrical resistance between places. You can have radioactive sources in it to be able to measure backscattering of hydrogen nuclei, which represent moisture contents. You can measure the natural gamma ray background supplied to the sonde, which is usually a measure of clays, which have radioactive elements in them. You could have a caliper log, which measures the diameter of the borehole to see if you have collapse in certain locations. And what else? Yeah, and you could have a spinner log. And so you could drop down a tool that has a little impeller on it. So if it goes down the hole in static water, then the velocity of that impeller would represent the velocity of the tool going down. And likewise, when you pull it back up, it would represent the velocity of the tool going up. So that's not very useful, because you know the velocity of the tool from the winch velocity. But if there was water flowing in the hole that was coming in at the bottom and going out somewhere at the top, then dropping it down and looking at the changes in velocity of that impeller as you go down and come up would give you a velocity profile within the hole. Actually, by subtracting off the downward velocity from the upward velocity would give you the net velocity. And so you could find out areas in your hole where water is gaining and where water is being lost. And that tells you something about the hydrogeology, so-called spinner logs. If you came to 303 class, which I know many of you didn't, you'd have heard that term before. Not looking at anyone in particular. Front row, right? Well, both actually now. I think the back row, they were keeners. I recognize those faces in 303. Front row, not so much. You said you didn't come.
I didn't go.
Yeah, fine. Yeah. Not a problem. So, we talked about spinner log. We talked about in terms of material derivatives. You might have heard it online. Uppercase D, V, dt, substantial derivatives. You measure the velocity on this impeller that's going down. That's not much use to you. You'd like to know the actual velocity of the fluid that you're going past, it's going through. And so you can use a substantial derivative to reduce that. I thought it was a good example at the time. And so by measuring these, you have to imagine these things on their side. So the long axis is the depth, and the magnitude that you're measuring is the magnitude as you go down the depth. So if you use a density log or a gamma log to measure the natural radioactivity, the electrical conductivity, electrical resistivity is just the reciprocal of electrical conductivity, self-potential, it doesn't matter. Then you can use, at a particular depth, you'd have all of these particular signals at a particular depth. You could use those to try and resolve exactly what the subsurface material was and make a guess as to whether it was a sand or a silt or a clay because of its particular characteristics. And so that's standard practice in petroleum. Don't know how it's used in environmental geophysics. Not very much. I think it's a bit too exotic. And of course, if you have a radioactive source in one of these sondes and your sonde gets stuck in the ground, then DEP or EPA would make you recover it because of its nature. So, and that happened to me once in Western Alberta, stuck in a hole. These are two tables at the end which talk about the utility of using ground penetrating radar, electromagnetics, electrical resistivity, refraction seismic refraction, magnetics, organic vapor analysis, so putting in a capillary, sucking out vapors from the soil and putting it through a gas chromatograph to see what's there. And I guess MD is walking on the beach when you're retired looking for coins. The same thing. So these talk about the applicability of these for all kinds of detecting all kinds of signals. Obviously, to pick up some material down in the subsurface, you have to have a contrast between the interfaces, and you have to have a way of being able to measure seismic velocity or resistivity or the dielectric constant in some way. The contrast in that gives you the location of the interface together with the travel times, and the magnitude of that parameter gives you some clue as to what it might be. So I think here must be 1 might be good, 3 might be doesn't work very well, and NA is not applicable. So you can see those. And a similar thing here for a bunch of different applications. Again with these same. Seismic prospecting, which we've talked about, monitoring for natural earthquakes. Sonar would be reflection seismicity, measuring gravity, as we talked about, a proton magnetometer, measuring resistivity with DC resistivity methods, car battery, electromagnetic radar is the main one, and these other exotic ones that we didn't talk about, and using sondes. We talked about all of them. So that's it. So that brings us to the end of the show. Is that not going to work? I don't know why it doesn't want to switch between these. Yeah, well, I guess I could do this. Don't zip up that bag yet. So, well, I was just going to do a kind of conclusions. You're preempting my conclusion. Well, fine. It's been great being with you for the last 8, 9, 10 weeks, right? This is the end of the 10th week. And so the whole essence of the class is to understand something about the transport of multiple fluids in the subsurface, and we've done that. We talked about single-phase fluids, dual transport of multiple phase fluids, the dissolution of those fluids and their transport, their retardation and attenuation if they're not conservative. Talked about the vadose zone in terms of understanding the physics. We talked about how we might find out what those distributions of the properties and those fluids might be in the subsurface from what we've talked about for the last 3 periods. And we've talked about how we might try and understand the transport of those materials in the subsurface, both in terms of how they get into their initial state that we find, and then how you might recover them by doing some remediation methods. And so it's all been geared to understanding the mechanisms by which transport occurs. And so that has to impact remediation methods in a big way. And so I guess my closing statement is that what we've tried to do in this is make some commentary about the mechanisms by which this occurs. And I don't know whether you used it or needed to use it, but we talked about this review sheet for the midterms. Actually, this is this whole course, which is included on this. You'll recognize capillary pressure saturation curves, relative permeability curves, plumes as they go downstream, Raoult's law, retardation, attenuation, etc. But what we haven't talked about is this final figure. It's a useful figure when you talk about remediation, because the transport of fluids, and we talked about it in site investigation, understanding the location of aquifers and aquicludes, high conductivity media and low conductivity media. Aquicludes act as barriers. We have to know some properties about those as to whether they're suitable capillary barriers, and aquifers act as conduits for flow. And so you might think that you could represent the behaviors of these systems on a chart that looks at the depth of the site that you're remediating versus some property such as permeability, which is the property of the subsurface. And so you can think about the different remediation methods, 4 of which you'll be looking at in your groups, and how well they would work in terms of the logic of transport in different conductivity materials, capillary characteristics in different conductivity materials, and their proximity kind of to the surface, right? We only get rock at depth. Some things like excavating you can't do with a backhoe in rock, and so some of these things only apply in shallow locations or in deep locations. And so if you look at the different methods that you'll look at, then you can kind of classify it on this chart. It's a useful chart to think about and to kind of frame this whole course into one particular